Okay, thanks everyone. So just some quick show hand. How many of you actually know something about BigDL? Cool. So yeah, in this session we are going to talk about BigDL and especially some of the latest features and use cases we have seen for BigDL. So just a quick summary of what BigDL is. It is a distributed deep learning library, a deep learning framework for Apache Spark. So if you are familiar with Spark, you should know there is various different components or libraries inside Spark, like SQL, R, streaming, MLlib, and so on, which all play very nice with each other and can be integrated as a coherent pipeline or solutions. And the BigDL is actually implemented as a standard library, just like MLlib and so on, so that you can use BigDL as a standard Spark library in your Spark programs and add deep learning functionalities to your big data applications. The goal here is really to make deep learning more accessible, much easier for our big data users and data scientists. Basically, you can write your deep learning applications as a standard Spark program. And then you can directly run it on your existing Hadoop or Spark cluster without any changes to your cluster. A lot of our early users are really, as I mentioned before, data scientists who want to who already play with big data on their existing Hadoop cluster, and they want to add some new deep learning neural network functionality to their applications, and they can easily do that on their existing infrastructure without anyone to provision for them or without any permission or any specialized hardware or software. So a lot of our users actually does that already. In terms of functionality, it actually provides the full deep learning functionality is basically feature parity with all those popular deep learning frameworks from Caffe, Touch, TensorBoard, and so on. And it's optimized for our big data cluster, which is usually runs on hundreds or thousands of large-scale Xeon clusters, and it is optimized for that environment with both high performance through various optimizations, Intel mass kernel libraries, multi-thread programming, as well as efficient scale-out. It leverages Spark for very large-scale distributed training and inference, and it also has some very efficient implementation of synchronous Mini-Batch SGD and all reduced type of communications on top of Spark. So why BigDL? We all know there is a lot of interest, a lot of excitement from the deep learning community, the deep learning research community, which bring out new algorithms and new breakthroughs in the use cases. However, for most of the big data users, they are actually really not deep learning experts. After we open source the BigDL, we get to talk a lot of those users. They are very interested in trying some of the new deep learning algorithms. But as I mentioned before, the average big data user, data scientist, analyst, who may write some streaming code, some SQL code, they are really not deep learning experts, and the existing deep learning tools are not really optimized for their requirement. And what we really want to do is really close the gap between the deep learning community and the big data and data science community by, again, making deep learning much easier for the big data and data science community. So our big data users can continue to use the familiar tools, the software tools, as well as the existing hardware infrastructure to build your deep learning applications. No specialized software or hardware infrastructure will be needed. And you can analyze your big data, the huge amount of data you stored on your Hadoop cluster using the deep learning functionalities directly on top of that cluster. We actually talked to a lot of the deep learning users, and today some of them actually are building those small, dedicated, specialized infrastructure to do deep learning. And for various reasons, but one of the, I would say, bottleneck, and probably people didn't talk a lot about that, is that how do you get the data? In a lot of cases, your data is actually stored on a distributed file system like HDFS, distributed across thousands or maybe tens of thousands of servers. And when you perform deep learning on a separate dedicated cluster, you need to put the data all over that 10,000 nodes through the network, which become one of the largest bottleneck for them. And again, the other part is you really can build deep learning applications as part of your standard big data or Spark application, and use all those standard workflow management tools they are already built for your big data workflows to manage that. And finally, as I mentioned before, you can directly leverage existing Hadoop cluster, Spark cluster you already have to run your deep learning applications. And as this is built on top of the standard big data architecture, it can actually be shared, dynamically shared with other users, with other applications, so that you run your SQL queries, you run your stream applications, your data warehousing applications, and together with deep learning applications on the same shared cluster, which improves your resource utilization and so on. So some quick overview of BigDL. Well, this is, as I mentioned before, it's essentially a distributed execution of either training or inference. And on the training side, it's nothing special. It's just like any machine learning or deep learning algorithms. It's an iterative process. You iterate through your data from 1 to n. And in each iteration, you get a mini batch of data, and then you do your training, which essentially is the forward-backward process, compute the gradient, and then you use some optimization method to update your weight based on your gradient. So it's an iterative mini batch synchronous SGD, and the code in the yellow box it can be actually easily get executed in a data parallel fashion, so that every task can compute a part of the gradient, and then you have a synchronous Mini-Batch SGD to update the weight. And for the inference part, it's very easy. I mean, the inference part is very embarrassingly parallel, so it can be easily distributed through your Hadoop big Spark framework. So that's how it is, right? It's a standard Spark job, no changes to the Spark Hadoop class needed. It's an iterative process, so actually every iteration of the training will run as a Spark job. And it's data parallel, so every Spark task runs on the same model, on a subset of your data. In the training, basically every Spark task will process a subset of your mini batch, compute the gradient, and as I mentioned before, you will run a synchronization after that and perform all of the SGD operations. So essentially, this is how a BigDL program looks like. It's a standard Spark program. You just call the BigDL library, which will generate a series of Spark jobs. Every Spark job will get distributed across your Spark cluster running on many different workers, and which will, again, use the BigDL library, and underneath we are using IntimeKL and other optimization to accelerate the compute. And again, there is no change needed for your cluster. It's just a standard Spark job. As I mentioned before, we are running a synchronous mini-batch SGD, and in Spark today, a lot of the machine learning algorithms it is actually built based on synchronous mini-batch SGD, but a lot of them are currently using a tree aggregation type of synchronization. So every node every worker, every task will send their gradient to a global node. In a lot of cases, it's a driver to synchronize the data, and it can do a tree type of aggregation. But again, this is not very efficient in terms of the bandwidth usage, as well as you create hotspot in your system and so on. So in BigDL, we are actually building a peer-to-peer or reduced type of synchronization, so that there is no single bottleneck. I mean, every worker is actually the same. So there is no bottleneck in the system, and we are directly built on top of the block memory in Spark. If you're familiar with Spark, it's a kind of a distributed in-memory cache system inside Spark used to, for instance, cache RDD data. So we leverage existing infrastructure in Spark and kind of use block manager as somewhat similar to a parameter server, but without introducing new modules or making changes to Spark. So everything works on the standard vanilla Spark distribution you can get, and we just directly leverage the block manager to build this high-performance, highly efficient synchronous mini-batch SGD. In terms of the APIs, I mean, specifically for deep learning, we provided first of Tensor, which is, if you're familiar with the ND array, it's very similar to ND array. It's just a multi-dimensional array of numeric types. It provides the generic support for those numeric computings leveraged into MKL, so it's actually highly efficient. I mean, it's much faster than those math than also the math libraries on Scala or using Scala Java. And then you construct a sample using the tensors. You have the input, your target. And we build a lot of the modules or layers, which essentially the different layers of the neural networks, like convolution, recurrent, Lulu, and so on. It's 100+ layers. As I mentioned before, it's actually at the same functionality level with those existing deep learning frameworks like Caffe or Touch and so on. Criterion is the loss function you have, and the optimizer, especially the distributed optimizer, is the one which implements also the synchronous mini-batch SGD. And you can use a lot of different optimal methods like SGD, Adam, AdGrad, and so on in your optimizer. So some examples how it gets used. As I mentioned before, BigDL is really a standard Spark program, so it can be seamlessly integrated with the Spark, with other components in a Spark library, like SQL or streaming. So in this case, we're showing that you can actually create a UDF using the BigDL. In that UDF, you can, for instance, load your BigDL model, and then you say you have a database of different images. And now, instead of querying the database using the name of the image or description of the image, you can actually get the image raw data, pass the raw data to your UDF, which in this case is defined as image classifier in BigDL, and using that UDF to process the raw data of the image, the pixel of the image, using the deep learning model you already built, and generate a label, for instance, and then you can query that label. In this case, you can actually select the other dogs from the image based on the pixel of the image. And so it's easier to integrate it with Spark SQL, DataFrames, or structured streaming in this fashion. And also, it can be easily integrated with Spark streaming, not only for inference, but also for distributed training or fine-tuning. In a lot of cases, you will get a pre-trained model, but as new data comes in, you want to update that model, and you can actually do it in a distributed fashion inside Spark streaming. And also, it's very straightforward to integrate that with ML pipelines and so on. Well, so that's the overview of the BigDL, and we open sourced the BigDL at the end of last year, and it's get a lot of I would say, healthy interest and usage from the community and our customers. And we currently, the latest stable version is 0.1.0, just released it beginning of April. And we are currently working on a follow-up release 0.1.1, which will coming out in the coming week. And our next major release will be 0.2, we are coming out soon. And if you go to our GitHub repository, there is a download page. You can get all those releases as well as our nightly build. So some of the features we're going to highlight in this talk. First, Python support. So we know that Python is one of the most widely used language in the data science community. So in BigDL today, we provide both Scala as well as Python. Python is built on top of Apache Spark, and we support both Python 2.7 and 3.5. And with that support, you can easily integrate the BigDL application in your notebook so that you can have a Jupyter notebook running BigDL on top of PySpark, and then which can underneath, it can actually automatically running on a large cluster in a distributed fashion. And we also provide some support so that you can, at least for young clusters, this is something about PySpark, right? PySpark is great, which allows you to use existing Python libraries like pandas, NumPy, and so on in a distributed fashion. So now you can distribute your data using PySpark, and on each partition, you can just apply your existing Python libraries, but it requires you to install all the Python dependencies on each worker you are running on. And we provide the necessary support for users to actually automatically packing all those dependencies for Young, so that there is no need to change it. Again, there is no need to change your Young clusters because sometimes it's not feasible actually to install your own Python dependencies on the node in your Young cluster. And we allows you to basically run your BigDL Python applications without pre-install anything on your Young cluster. We also provide integration with the TensorBoard, which is yes. So default, we have Scala API and Python API if it's not clear before, And we also provide the integration with the TensorBoard. It's a set of tools from Google for you to visualize the deep learning applications, and now you can use BigDL with TensorBoard, and you can use TensorBoard to visualize, for instance, your learning rate, how your learning changes, how your gradient distribution looks like, and so on. There is many recurrent unit support provided in BigDL 0.1. As I mentioned before, we are currently working on BigDL 0.2, which will be our next major release. It will be available pretty soon. And in that, we are introducing functional API just like those in Keras and PyTorch. You can using functional API so that in this case you can actually it allows you easily to construct a graph using those different layers or modules, and it's much easier to construct complex models using those functional APIs. For instance, if you have a multi-input, multi-output models and so on, it's actually much easier to do that in your functional APIs. And we are adding that support in our BigDL 0.2 release. The other part we are our user actually asks a lot is the kind of a model interpretation. Basically, you can now using BigDL to load a TensorFlow model, Caffe model, or Torch model directly into BigDL so that you can use that in your Spark analytics pipelines. It can be used for some examples of transfer learning. You get an existing model, you can and then you can do in some fine tuning, for instance. A lot of our use cases, actually a lot of the existing deep learning applications using existing model and then add new data to train the model in a distributed fashion, and you now can do that in BigDL, and you can load pre-trained model from other frameworks as well. And we can also generate models so that it can be loaded into TensorFlow or Cafe or Touch for various operations. And the other part is really you can now also run BigDL as a standard local Scala program on your local JVM without Spark, which will make it actually easier to deploy your model. I mean, a BigDL model can now be easily deployed in, for instance, a Java application servers. You can just use it as a Java program. Well, there is various advanced deep learning functionality when adding recurrent dropout by directly on TreeSTM, which is actually some of our users are using the TreeSTM to build those sentiment analysis type of natural language processing. And there's also 3D convolution, which is pretty important for a lot of the medical imaging processing. And convolutional STM, which is used in, for instance, in weather forecast. You get a series of radar images, and you want to predict the other means another series type of radio images to do the weather forecast. Yeah, so those are some of the latest use cases. Just some quick examples of how BigDL gets used by our users for different applications. As mentioned before, BigDL is built on top of the, well, I would say cloud architecture or big data architecture, which is measure parallel, scale out, automatic fault tolerant, elasticity, resources sharing, and so on. So it's gets very good adoption by those cloud providers like AWS, Azure, Alibaba, as well as those big data platforms like Cloudera and Databricks. They actually provide very support and tutorials for running BigDL on their platform. So if you're interested, you can check the link there on their website. And one of the interesting use cases our user is working on their big data platform, for instance, on a CDH cluster, is to do a lot of recommendation. And recently, there is a lot of new results by combining deep learning or neural networks with your existing more of the classic machine learning models, such as matrix factorization or logistic regression in the recommendation, so that it can provide a better result. So in this case, neural capture filtering is combining a neural network with a matrix factorization, ALS type of matrix factorization model to produce a better result. And in the other one, the wider deep learning is combines the logistic regression with a neural network to generate a better result. The other interesting example use case people are building on using BigDL is to do some type of churn analysis. It's essentially build a recurrent neural network to predict the time to event, basically how long before the customer will churn. This is one particular customer we have been working with for some time, the UnionPay, which is kind of the Visa in China, but it's probably larger than Visa. And we are working with UnionPay, and they are building a end-to-end pipeline for fraud detection on top of the Spark pipeline using CDH. So it's actually a very complex end-to-end analytics pipeline from data management to other feature management, feature engineering, selection. And then you do model training. In this case, we are building an ensemble of 10+ neural networks. And then you do various research and fine-tuning, cross-validation, and so on. It's all need to be integrated with those end-to-end ML pipeline. Just talk about that. This is one use case people are using the TreeSTM to build sentiment analysis for those natural language. Right. And then there are some interesting new use cases like speech recognition as well as the image recognition, which you can basically recognize the object in your graph in your pictures. There is a talk from Intel tomorrow, I think at 5 p.m. Which I hope you can stay late for that talk, which will talk details on how we are working with our users to build those speech recognition as well as image recognition pipelines using BigDL on top of Spark. This is one example, actually, for the image, one direct application of the image recognition. In this case, there is a very large manufacturing and customer taking pictures from their manufacturing pipeline and try to recognize defects in their pictures using the BigDL pipeline. So it's, again, an end-to-end complex index pipeline from the image injection to image processing and so on. And finally, we have been working with some of the 3D medical images using the 3D convolution type of processing. So, well, that's all I want to share in this session. And there is we are open source on GitHub. So if you're not, I will encourage you to check out our GitHub. And we also have a Intel developer zone you can check out for all the information from Intel about what we are working on AI. Thank you.
Thank you, Jason, for such an informative talk. And right now, I think Jason and Radhika are ready to take questions. So if you have any question, please approach to this mic. So I will hand.
Yeah, just one more thing to add on. So you saw this morning we have announced a free compute for BigDL. So that's BigDL / free compute for BigDL. Is that what it's called? It's software.intel.com. Compute, yeah. So if you have an interesting idea, interesting app you want to build on BigDL, submit your application.
Okay, well, thank you. Great talk and great work. So with the initiative that was announced by Mathieu this morning from Databricks, where do you see this work going? Because it seems to be very common goals, which is simplifying the API, integrating the pipeline, and parallelism, utilizing Spark parallelism. So are these two works going to merge? They're going to separate? Well, how does it compare?
Yeah, we actually have been talking with Databricks on that. And I think basically it is, again, a pipeline for you to load different deep learning models by different frameworks. And actually, it's very easy to do that for BigDL, because BigDL is a standard Spark library. You can easily plug into that. On the other hand, the unique advantage of BigDL is that for those external, Databricks is doing that because the existing third-party frameworks is difficult to use in Spark, and the new pipeline will make it easier, but it only works for instance, inference, as well as very small model tuning, because you can only tune the model on a single node without a distributed training or tuning. You cannot do a very large scale distributed training or distributed model fine tuning. You can only do a single node based processing, which is fine for inference and fine for very small model tuning. And the uniqueness for BigDL is that it's built into the Spark framework and allows you to do very large scale distributed model training, fine tuning, as well, in addition to those inference and so on. So I think that efforts actually acknowledge it's very difficult to use deep learning, existing deep learning frameworks in Spark, in big data. And there's some help provided by those new APIs, but it's only a small subset of problem. And BigDL try to, if you're using those external frameworks, but BigDL try to build a native, I would say, a library native for Spark so that you can solve the problem much more naturally.
But another thing to add might be, Jason, that they are not trying to reinvent the wheel in terms of building core DL functionalities.
Yeah, they are just plugging existing frameworks like TensorFlow, Keras, maybe BigDL. It's actually pretty straightforward to do that.
Jason, great talk. This is Andy Fan from Yahoo. So we have been, thanks for trying to address the challenge to apply the deep learning on the big data environment. And I did, when I was looking at your things and comparing the work my team has been working on, the Cafe on Spark, TensorFlow on Spark, I wonder why you take the approach, you try to do, essentially you are reinvent a view for deep learning in the big data environment, right? Because the setup of the library you try to creating is more or less the same, you are kind of, in some way it's catching up whatever the Google guy is doing on the TensorFlow. And so I just wonder how you compare with the BigDL, like with the, let's say, distributed TensorFlow, all those other efforts. And like for the performance point of view, and then long-term, the community development point of view.
Well, I think first of all, we actually, as I talked before, we actually provide support for the models which, well, you can use the TensorFlow model, Cafe model, and the Touch model, and so on, directly inside BigDL. So in a way, we are a superset of TensorFlow and Cafe and Touch in terms of functionalities. I don't think we are directly comparing with the TensorFlow and so on, but in terms of functionality, we're really a superset of those functionalities. And and our real focus is really, I would say ease of use for big data users, because you really don't need a specialized software or hardware infrastructure to run those frameworks. I think TensorFlow, Cafe, or Touch has their interesting functionalities, a lot of functionality and a lot of communities, but I would say a lot of the deep learning communities and the big data communities, there is a gap, and we want to address that gap.
Mm-hmm. So then more specifically, let me ask a question then. In your talk, you mentioned the synchronous distributed learning, right? Mm-hmm. So how about the other side, the asynchronous learnings in the...
Yeah, we could do that, but I think the common wisdom in the industry today is that it's very difficult to converge for very complex deep neural networks using asynchronous SGD. So we currently focus on synchronous SGD because it's much easier to converge than asynchronous SGD. I think how you do asynchronous SGD, especially for very complex, very deep neural network, is kind of open research area today.
And how about GPU?
Currently, our focus is on existing big data infrastructure. As I mentioned before, we want the user to directly leverage their existing hardware, software infrastructure without any change. So our current focus is really optimized for this type of platform. So it's highly optimized for existing Hadoop cluster.
We can let these two finish.
It's our current focus.
Thank you.
Okay. Sorry to interrupt, but we probably just have 2 minutes for the questions, and maybe you can talk offline with Jason and Radhika. Yeah.
Sure.